All right. Hello, everybody. Today we are going to be talking about geometric series. So, in the past couple of lessons, we've talked about arithmetic series that are adding by the same number every time. What's going to happen here is we're going to start exploring, well, what if we multiply by the same number every time? How do we add things like that up? And so I'm just going to take a moment to read our lesson introduction. So it says, in this lesson, you will work with geometric series and develop a method for representing and calculating sums of geometric series. Being able to calculate the sum of a geometric series allows you to calculate how much a long-term loan will really cost or how much you will end up paying for something when you buy it on credit. As you work with your team on the problems in this lesson, keep the following discussion questions in mind. Can we use any of the strategies we already know? How can we use what we know about systems of equations? That's going to come up when we develop the formula, by the way. How can we describe what we have done? And how can we generalize what we have done so we can add any number of terms that are multiplied? Okay, so the first problem we're dealing with is number 81, and it says Caroline is helping her younger sister Julie with her math homework. What I want you to do is I want you to pause this video and take about 5 or 6 minutes to try it in your teams. Okay, so problem A says Julie was given the sequence 10, 50, 250, 1250, 6,250, and she writes this equation. T of n equals 2 times 5 to the n and makes this graph at right. Caroline says suddenly, no, you've written the wrong equation. The correct equation for the sequence is T of n equals 10 times 5 to the n minus 1. Is Caroline correct? So one way we could verify this is we can look at this graph over here, and we can see that the first point we have here is displayed here. It's a 10. So we want to get 10 when we plug in 1 because this is the first term. And so we are checking Caroline's equation. And she has this. And if I put in a 1 here, I have 5 to the 1 minus 1, which is 0. Anything to the 0 power is 1. So 5 to the 0 is 1. And I have 1 times 10. So it looks like her first term is coming out correctly, but let's just check that second one. If I plug in 2, I should get 50. So 2 minus 1 leaves me with an exponent of 1. 5 to the first power is 5. And 5 times 10 is 50. So it looks like that pattern's working out just fine. How about Julie's equation here? Let's do the same thing. If I plug in 1, I get 5 to the first power, or 5. And 5 times 2 is 10, which is the first term. And then if I plug in 2, I get 5 squared, which is 25, and 25 times 2 is 50, and so on. So it looks like, again, we have two equations that work. This is in zero-term form, where we have the zero term, something that's not shown up here. Since this is multiplying by 5, to get that, you would need to divide by 5. Okay, so that's how they're getting that 2 there, times 5 to the n. So these are kind of like your y equals mx, not mx plus b, a times b to the x equations, an exponential situation, but instead of using y and x, they're using t of n and n because, again, we're not connecting dots here because we can't have partial terms. So I can't say, what's the 1.5 term in this sequence? But they're following this structure here. This is our first term form. So notice that you're starting with 10, which is the first term. And then instead of using n, they're using that n minus 1. So similar to the arithmetic sequence notation, but just here in the geometric sequence. So let's talk about the advantages of writing it like Caroline did. This is nice because it gives us the first term. But again, this equation might be nice because it gives us more directly. We don't have to do that n minus 1 thing. So it's just kind of one more step that you have to do. What you had to do here is you had to write equation, this one, t of n equals 18 times 3 to the n using Caroline's approach. So it looks like we need to write that in first term form. So to get the first term for this, we would plug in 1 for n. And so we have 18 times 3. And if I multiply that, looks like I'm getting 54. So I have t of n equals my first term, which is 54. The multiplier of 3 doesn't change, but my exponent is an n. It's n minus 1. So that's what you should have gotten for C. All right, so we're going to get into a fun problem in 82. Just going to clear this screen real quick and scroll down. All right, so what we got here is a lottery problem. And we're going to pick a payout. And here's the first part of the equation here. So let's take a moment to read this. It says, with the record-setting lottery jackpot projected for noon tomorrow, Mr. Hanks is standing in a very long line to buy a ticket. The man behind him in line taps him on the shoulder to ask, "Have you thought about how you'd spend the money if you won?" Before Mr. Hanks can answer, the woman in the front interrupts and says, "First, you have to decide whether you want to get your earnings in one lump sum right away or if you want to receive them over time. I'm sure one option must be a better deal, but I haven't figured out which one." And just a side note, this is true. You can choose to do either one of these options. So when Mr. Hanks gets home, he immediately goes online and learns that lottery winners do have a choice: receive the winnings in a single payment of 51% of the jackpot right away, or spread the payments over the jackpot over 20 years. So you might be wondering why only 51%. Well, if you win the lottery, it looks like almost half of it goes to taxes. So that's kind of fun. All right. So he also learns that the jackpot is projected to be 50 million. He knows that he takes the single payment, he can invest it right away and earn 4% annual interest on that money. If he chooses to receive the payment over 20 years, the lottery commission will invest the money for him. They guarantee to pay $1,500,000 in the first year to increase the amount they pay by 5% each year. At lunchtime, Mr. Hanks walks into your class and asks for your help. If your team can figure out the difference between the totals for the two payment methods, Mr. Hank will give that amount to your team if he wins the lottery. All right, so I always like to do this to start off. So pause this video for 1 second. I want you to just talk for 1 second. What would you want to do? Would you want to take the first option, which is just taking a payment of 51% of the money and then just like investing it on your own? Or would you want to receive the payments over the 20 years where they each get 5% interest? So talk about which one you would personally want, because that might be a you question. Are you willing to wait 20 years for your money? Or is this something that you're going to want more immediately? And then another question I want you to discuss is which one do you think will make more money? Okay, so take about 1 to 2 minutes, have that conversation with your team. Okay, so now that you've had the discussion, let's go and answer these questions. So question A says, if Mr. Hanks wins the lottery and takes the payments over time, the amounts he will receive each form a geometric sequence. What is the first term? The first amount of money he will get is that 1.5 million, okay? So that will be his first term. And then it looks like that we have a multiplier. So it says he earns 5%. So 5% as a decimal is 0.05, but then we have to add the 100% to that. So 105% as a decimal leaves us with a multiplier of 1.05. That's the answer to part 2. And then it says write an equation to represent the terms as a sequence. So I personally want to use the first term form here so then I don't have to do any extra thinking. So the equation we could write is T of n equals, and I'm just going to come down here because I'm running out of space. So that 1.5 million times 1.05 to the n minus 1 to make that first term. So if Mr. Hanks takes the payments over time, how much money will he receive in the 20th year? So to do that, we're just going to plug in 20 for this. So I'm just going to quick go to my calculator. Maybe you want to do this too, just to make sure you're getting the same thing as me. So if we need to pause and get calculators, if we don't have those, go ahead and do that. So I'm just typing that in, 2, and I'm going to use the 19th power instead of doing 20 minus 1. And it looks like I am getting 3,790,000 $1,425, and we'll call it 29 cents. Okay, so that's how much money he will receive on the 20th year. Okay, so when you add up the terms of this sequence to determine the total over the 20 years, you are calculating the sum of a geometric series. So it asks us to show the geometric series. So remember, we want to start with the first three terms plus ... plus the last term. So the first term in this sequence was that 1.5 million. Okay, and to get our second one, we can just multiply by the 1.05, and I have these numbers written over here. So 1,575,000 is our second term. And then our third one, again, multiplying by 1.05 gives us 1,653,750. At this point, now that I have three, that I can see that common multiplier happening, and I have made a mistake. It says you want to add the terms in the sequence, show the geometric series. So I'm accidentally writing a sequence instead of a series. So I do apologize. These should all be plus signs because I'm writing the series, not the sequence. Okay, so change those to plus signs, ... plus, and then you need your last term. And that's what we generated right here by plugging in 20 for n. So that's that 3,790,425.29. Okay, so with your team, discuss a strategy for calculating the sum without having to calculate and then add all the 20 terms. So this would take a very long time again because I need to keep multiplying by 1.05. And then once I do that, I have to add these 20 terms up. Okay? So it says, consider the graphical method of creating rectangles that you used with arithmetic series. Can we do this with arithmetic series? Remember, our formula for that works because we're adding by a same number every time. So if you can imagine those rectangles, and we could cut it in half, or we could stack them on top of each other because they were going up with a common difference. Will that work for a geometric series? Okay. So talk about if you think that is going to work or not. So I'm going to pause this for a second. Okay, so hopefully you had some sort of a discussion. Sometimes it's nice to look at some concrete examples if you weren't quite sure. So before looking at problem 83, I just want to say, hey, here's some examples. Will the arithmetic pattern that we used before work? So if I add the first and the last term, remember I have to be getting the same thing. So if I add 2 to this 6,250, I get 6,252. And then I add 10 to the 1250. Well, that's not the same thing. And then 50 plus 250, that is not the same thing. So I can't use the arithmetic series formula that we've been working with because it's not adding by the same now. Now there's a nice pattern, but it's not adding. So we can't use that stacking idea that we did before. So we're going to have to use some other ideas. So now we're going to get into problem 83, and it says, well, working on the strategy to solve the lottery problem, so land teams to tried to look at an easier equation with fewer terms. So instead of looking at the lottery problem with 20, sometimes we break things up into smaller things to make sense of this, and then we're like, okay, let's use this on the larger picture here. So it looks like we have this sequence here where our first term is 2 and our multiplier is 5. So they write out the first 6 terms in the sequence, and they call the 6 S6, meaning the sum of the 6 terms, and then write this equation here. And then Luann remembers the algebraic strategy for calculating the sum of the arithmetic series, where she added the sequence onto itself and then manipulated the resulting equation. Is there a similar method you could use for a geometric series? Is there a way to write the equation down twice and then rewrite the second equation to eliminate some of the terms? Okay, so we're trying to get rid of some stuff. And so take 2-3 minutes. Could you figure out, and let's read what she's saying again. she says she remembers the algebraic strategy for calculating the sum of an arithmetic series where she added the sequence onto itself. Okay, so we got to add it onto itself at some point. But then we also need to manipulate the equation so some things are canceling. And so I want us to think back to the lesson introduction where it said, do we know anything about like systems of equations? So like ways we can cancel things out. So maybe that gives you some hints as to maybe what we are doing here. Okay, so I'm going to go ahead and pause this video so you can talk about a strategy. What do you guys think? All right, I am going to come here to talk about this strategy. There's no nice way to get my smart files on this recording. So looking at problem 84, you kind of talked about some ideas, but this is what we're going to do. So this Luann reports to her team. I'm sure this can be simplified, but when I try to add a series onto itself, as we did in the arithmetic series, it just gets bigger and bigger and bigger. And there's no clear pattern. If I subtract it from itself, I'm left with 0 equals 0. So what are some techniques that you've used for writing an equation when solving a system of equations using the elimination methods? And can these be applied to the situation? So one of the things we've done is when you're trying to eliminate something, but you can't eliminate them directly, you multiply one of the equations by a multiplier. And so that's what we're going to try here. So she gets this idea. So she writes out this sum, and this is small enough that she can add it together. She knows this is 7,812. And this is what she came up with. So she says, look, I multiply both sides of the equation by the sequence multiplier. Luann is really excited about the result. How can you use her results and combine the equation to calculate the sum? So what she does is she takes the original sum and she multiplies it by 5. Okay, so that's why we have this notation 5s, 5 times the sum. And so she rewrites this stuff. She just distributes this 5 to all of these things, and she gets this here. Okay, now elimination. We're eliminating items. So then what she does is she subtracts the original sum. So notice that's exactly what she has right here. And she staggers it in a way that the 10s are stacked, the 50s are stacked, the 250s, 1250s, and 6,250s, okay? So she's subtracting them. So there's no term here, so we have like kind of like this 0 minus 2. So we have the first term, we have the opposite of the first term. Now, all these things are going to cancel because 10 minus 10 is 0 and 50 minus 50 is 0, etc., until we get to here. Then we have 31,250, which is the last term multiplied by 5, which is the series multiplier. Okay? Right here, we have 5 times the sum, and we're subtracting the sum of itself just one time. So we have 4 times the sum. So we have the multiplier of the sum, but 1 less than that. So that's what's happening here. She adds these things together. Just going to slide down here so you can see all of it. She slides these things down here. She adds these together. She gets this equals 4s, divides both sides by 4, and gets the sum. So now what we need to do is we need to come back and we need to figure out how can we generalize this to everything. And so keep in mind what's happening here. She has the opposite of the first term. Okay, so if I'm generalizing this, the opposite of the first term. She has the last term equals 4 times the sum. So that's 1 less than the multiplier. I want you to pause this and I want you to try to write an equation that simplifies all of this into nice math terms that you could use to maybe figure out the lottery problem, okay? Okay, so let's see what you guys came up with. So I'm just going to call this S of n, so the sum of your number of terms. So in this case, we would have put a 6. but we can just say any number, right? Equals, now we have opposite of the first term, and we have this multiplier times the last term. Now, for simplicity, sometimes it's nice not to have that negative in front. So you're going to see mathematicians flip these things around because addition and subtraction can be flipped. And so you have the rate times your last term, okay? So your last term in this case is 6,250. So our rate times our last term. We can use this notation for that, T of n, okay? So the rate times the last term. We're getting a lot of parentheses here. You don't need all three of these parentheses. Just know that you're multiplying this first. We're going to subtract the first term. And we're going to take this over because we divided, right? We're going to take this over our rate minus 1 because it was 5 minus 1 to get there. We divided by this. So this is the equation that we looked like. And if we're going to see it nicely here, like I said, we don't need this obsessive amount of parentheses. So let me just get rid of that. I don't know what I was doing there. All right. This. And we don't necessarily need these parentheses because order of operations says multiply first. But I'm going to put them there because I can tell you from experience, for whatever reason, students do not multiply this in the correct order. And a lot of students get these problems wrong on tests because they, for whatever reason, take the last term and minus the first term and then multiply it by the rate. But you need to do the rate times the last term minus the first term over the rate minus 1. And I'm actually I'm just going to scroll down here. I'm going to take a moment to write this in words as well. So this might make more sense to you if this notation is kind of scary. So what this is the sum of terms equals your rate times your last term. And you're going to do that first, minus your first term over the rate minus 1. And I think this is a great time to pause this video right now and put this in your green notes. And you could put both of these. Put the equation with the math notation that you'll see, but also if that's confusing to you, put it in words and then start making the connections between the two and then understand the shortcut, that shorthand notation that mathematicians use. Okay, so take a moment, pause, get this in your green notes. When we talk about infinite series tomorrow, that formula is going to stem from this one. So make sure you have this and understand this and talk about it with your teams. Okay, so we're going to come back to our textbook here, our ebook, if you're following along there. The first problem we're going to do is basically, hey, do you understand that formula that we just worked with? So we're going to do problem 86. If you do not have the handout for this, now's a good time to grab that. So if you need to pause this video, feel free to grab those from the sub. But what we have here is problem 86, where it says Antonio is working with a new geometric series generated by this equation right here. His sister challenges him to compute the sum of the first 37 terms. He needs your help. So we're going to show how he can figure this out with any number of terms without adding them all up. And what is the first 37 terms, okay? So pause this video. Make sure you can use the formula. Make sure you can type this into your calculator, okay? So here is what we have. So maybe just like access your green sheet. This is how he would be able to add up. It says any number of terms first, okay? So the equation that we're going to have is, remember, it's the last term. Now, in this case, his last term is this, and we're going to take it times the multiplier. So 1.2 is that rate, okay? So the rate times the last term, well, that's going to be just generated by this equation, okay? And whatever I put in will give me the last term. So that's this generalized minus the first term, and the first term here is this 30. And then that's all over the rate, which is 1.2 minus 1. Okay, so this is just the equation. The equation generates the last term. Now you need to figure out what the sum of the first 37 terms is. So all I'm doing is taking this n and putting 37 in it because there's going to have 37 terms. Like I said, practice this in your calculator. So I hope you tried this on your own. What you should get here is 127,434. So if you aren't getting that, check your parentheses, check your equations, see if you're doing all right on that. It says, now Antonio's sister challenged him to calculate the sum of the 38th through the 99th terms in the series. Work through this on your team. We're just going to go ahead and skip this problem now. We're going to address problems like this later. So just go ahead and skip C. This isn't on your resource page for now. We're going to go and talk about problem 87, picking a payout, part 2. So what is going to get us more money in this lottery problem? Okay, so look at our options here. Let's just remind ourselves of the two options. So option 1 is to receive a single payment of 51% of the jackpot right away and invest the money at 4% interest compounded annually. The second one is to receive payments once a year for 20 years, with the first payment being $1.5 million, and the payments will increase by 5% each year. So this is the adding one. We're going to be using that geometric series formula that we just figured out. Option 1 is just a geometric sequence equation where I'm simply just plugging in the 20 for n in my equation and how much total money do I have, because I'm leaving it in there and I'm just letting it compound year after year after year. Okay. Okay, so how much money will he receive for this? So we're going to take the $5 million that he would get, and we're going to multiply it by 0.51. That's going to be his take home right away. And so he has $25,500,000 if he does that, okay? But he's going to invest this money, okay? That means put it in the bank, don't touch it. So how we can get how much money he'll have with this 4% for 20 years, we're going to start with this. Now, this in this case is the zero term because we're putting this in right away. And after 1 year, how much does he have? After 2 years. So this is actually a zero term in this. Times the 1.04 times this quantity here, we can put 20 in, okay? And so if you type that into your calculators, he will have $55,873,640. Is this the sum of a sequence? No. We are just plugging 20 in to a geometric sequence equation, okay? So now we're going to deal with one where it is a series. We're going to be adding up all of those terms. So I'm just going to scoot this down here. So now we're going to suppose that Mr. Hanks chooses the payment over 20 years, starting with the payment of $1.5 million. How much money will he receive on the second year, on the 5th year? So we kind of did this earlier, right? So he's going to take that 1.5. To get the second year, you do times 1.05 times 1.05, or, here's our first term. To get our second term, we could multiply it by that once. To get the next term, we'll do it twice, right? So we're using this equation to get me there, okay? So again, this is the equation that we'll use to help generate any money in a given year, but we want to sum it all up. So we're going to use that formula that we talked about earlier, where we take, and I'm just going to clear this for simplicity here, so I have more space to write. So we're going to take that rate, which is need a pen. We have that rate of 1.05 times the last term. Now to get that last term, we take that 1,500,000 to our multiplier to the power of n minus 1. So that's 20 minus 1. So that will get us our last term times the multiplier and then minus our first term. I'm running out of space, but 1.5 mil. So understand that that's the same number as this. And then I'm going to divide that by my rate minus 1. So 1.05 minus 1. So go ahead and type that into your calculators. Make sure you can get this okay. In doing so, he gets 49,598,931. So coming back to what should he choose? Well, in the first option, he makes more money. And that might be a surprise, right? Maybe you're like, oh, we're talking about series. He would make more money in this. His interest rate is lower here. But, keep in mind in both of these options, the first option, he has to keep that money in the bank for 20 years. And can't touch it for 20 years to get that amount of money. And so maybe you're a person that's like, hey, I would want to do option B because then I get 1.5 million and maybe I do something with that. So this is kind of like a preference thing on what you want to do. Okay. So, which one's going to get him more money, the lump sum and invest. And then the goal of this problem was to figure out by how much more. So we're going to take that first answer that we got. I'm just trying to pull this from my previous page, was the 55,873,640. And we're going to subtract this number right here. So in doing so, this is how much more money he would make, just like $6 million more. So like in the grand scheme of things, not that big, right? Yeah, so this is like the difference between those two things. Okay, so at the bottom of your resource page, you have 5 practice problems. Go ahead and practice those. I will try to put the solutions for you on another video so you can look at those and play with those a little bit. Working with that sigma notation that we worked with yesterday, which I know is still kind of new. Yeah, try those out on your own first and then go and check your answers. I hope you all have a great day.